start the recording. Sorry about that. Yeah, because we switched around the objectives. Remember, we had already done the question on how to calculate relative abundance. And so that's why it's here as it is. But we'll cover half of this objective, explain the phenomenon of radioactivity this evening. And tomorrow is a national holiday. I don't know if we get to meet to finish the other half, but we'll do the other half and then cite the use of radioisotopes in the other session. So to begin, what can you guys tell me about radioactivity? Anything at all? Just let me know something from each person about what you know of radioactivity.
Okay, sir. Good night. Radioactivity is basically the decay of um, unstable atoms that releases radiation.
Okay. And Jamal is saying in the chat that it is the process by which an unstable atomic nucleus loses energy by radiation. Go ahead, Fish.
Um, Radioactivity is the spontaneous disintegration atomic nuclei of an atomic nuclei that releases radioactive emissions, something along that line.
Right.
So I
So it's
think
going.
emphasis on the word spontaneous.
Why are you emphasizing spontaneous? What does that mean?
Because it is something that we can't predict. It's kind of spontaneous, something along that line.
Okay. So the correct thing to say is if you're using it's going to be of a radioactive nucleus. And then the plural is nuclei, right? So radioactive nuclei or
Thank you for that, sir.
right, great. Um, why does this happen? You guys have an idea of what radioactivity is? It's where the nucleus spontaneously emits radiation. Um, does this happen for all atoms? Like any element I can pick and it's going to undergo radioactive decay, or does it only apply to certain atoms?
I would like to believe that it's just certain atoms.
Certain atoms. Kiana, what do you think? Do you think it happens for all elements, all atoms, or just certain?
No, sir. I think it only happens with certain elements, and those are elements with an unstable atomic nucleus.
Okay, absolutely, absolutely great. Devishkar, you want to say something about radioactivity? Devishkar, are you there? And Devin, would you like to say something about radioactivity? Okay, it seems as if Devin and Devishkar are not here. Um, okay, all right. So, oh, sorry, Devishkar is saying that it is the decay of certain elements in which there is a nuclear decay. All right, Devishkar. Um, so, what we'll do in the introduction is that just as when we looked at the development of the atom, there are certain persons who we associate with the development of the atom. Can we just quickly recall some of those persons? Just the names. I don't need to know their contribution, but just the names of some persons who are associated with the development of the atom.
John Dalton,
John Dalton. Okay.
J.J. Thomson,
J. Thomson.
Ernest Rutherford,
Ernest Rutherford.
Neil Bohr.
Niels Bohr. Um, Devin is saying also Neil Bohr, and Divishkar is saying James Chadwick. Great. So those are some persons who are associated with the development of the atom. Can you tell me some persons who are associated with radioactivity?
Marie Curie,
Marie Curie, right? That's absolutely correct. So let's get into it. In the year 1896, French scientist Henri Becquerel was experimenting with a material. And so what he did, again, this here is in the, sorry, this here is in the year 1896. And so what he did was place a sample in, in the sun and then cover it with a photographic film. After some time, what he realized was that the photographic film had an image of the material that was placed on it. Now, around that same time, German scientist Wilhelm Röntgen discovered X-rays. And what Becquerel thought was that the material he had collected rays, absorbed rays from the sun, and then emitted it in the form of X-rays onto the photographic film. Remember, the thing about X-ray is that it allows for an image to be produced when it passes through. So when you go to take an X-ray of a bone or a part of your body, an image is actually produced on a film that the radiologist can read. So he had thought that this substance had actually absorbed sunlight and then given it off in the form of X-rays, and that is how it was able to be displayed on the photographic film. While conducting this experiment for a few days in Paris, because he's French, the weather was cloudy. The sun was not visible. And so he placed the radioactive sample, which is actually uranium, in a drawer along with the photographic film. And to his surprise, when he removed the radioactive substance and the photographic film from the drawer, he noticed that the same image was produced or was formed on the photographic film. Now, the drawer didn't had any form of sunlight. So that got Becquerel confused. It could not have been then that this material, this substance was taking in sunlight and giving it off as X-rays. Because in the drawer, the photographic film and the material were in total darkness. And so that led him to believe that this material, this substance was actually giving off something instead of off of its own, rather than absorbing it from the sun. And he termed that thing that this material was given off Becquerel rays after himself. Becquerel rays, that's what he called it. He named this after himself. So far, so good. Do we have any questions? Can I have a feedback if that was clear?
was absolutely clear, sir. Thank you.
Okay. Amy? All right. Yes, Shannon, that's clear. Devin, Devishkar, Jamal, Kiana, is this clear so far? All right, great. So moving on. A few months after Becquerel's discovery, Polish scientist rather, Marie Curie, along with her French husband Pierre, were working with some uranium samples. And what Marie Curie discovered is that the amount of radioactivity or the radiation level of the uranium was only dependent on what is inside of the uranium itself and not from external factors. External factors would be things like temperature and pressure and volume and sunlight and all of these things. And it really did not depend on any of those factors, but rather only on what was within the nucleus or within the atom itself. In fact, she had won a Nobel Prize in chemistry for this discovery, right? And so that's a very important discovery, that the amount of radiation depended only on what was inside the nucleus, inside the atom. It was independent of all external factors. And two of her other famous discoveries were actually two other radioactive elements that were way more radioactive than uranium itself. She found one that was around 300 times more radioactive than uranium, which she named polonium, which is this one here, after her country, Poland, right? Remember, she was a Polish scientist, so she discovered polonium, which was about 300 times more radioactive than uranium itself. And then also, she discovered radium, which was 900 times more radioactive than uranium. So this was her important discovery, especially this one here, that the amount of radiation depended only on what was happening inside of the nucleus, and then her discovery of these two radioactive elements. Now, she did not know the dangers of radioactivity and radioactive elements. And it was actually from working many years with radioactive elements that actually led to her death. Right? She died because of the amount of radioactive emissions that she was exposed to over the years that she was working with radioactive isotopes or radioactive elements. Another person, or the third person who contributed towards radioactivity, is a returning character actually, who dealt with the development of the atom, and that is New Zealand scientist Ernest Rutherford. In 1899, he was actually working in Canada with the Becquerel rays, right? Those same things that were discovered by Becquerel, the Becquerel rays. He was working with them and with uranium, as the uranium was emitting the Becquerel rays. And he found that the Becquerel rays was not just one thing, but was actually two different types of particles that were emitted, alpha particles and beta particles. And later on, he figured that there was also third emission in the form of electromagnetic waves, or electromagnetic wave carry energy, right? So that's what, and so he named them actually alpha particle, beta particle, and gamma radiation. And this was before he actually discovered that the atom had a central nucleus with electrons orbiting, and then that majority of the atom is empty space. Because remember, he had shot this, an alpha particle, towards the gold foil. So it must have been that the alpha particles were actually discovered way before that gold foil experiment happened. But he was the one that actually figured out that the Becquerel rays were, were three different types of things. Two of them are particles and one of them is a form of energy. And so if we have to define, we would say that radioactive decay or radioactivity is the process. Now, it's very important that you understand the term that you are defining. For example, when we talk about melting point, right? Melting point. And you're defining melting point. You don't say melting point is the thing, or melting point is when, or melting point is where. Melting point is a temperature. So you say melting point is the temperature at which a solid changes to a liquid or a liquid changes to a solid. When you talk about specific heat capacity, you don't say specific heat capacity is when and specific heat capacity is where. Specific heat capacity is the energy. It's an amount of energy that is required to do something. So in the same way, radioactive decay, it's not temperature, it's not energy, it's not molecules or whatever, but it's a process, right? It's a process during which unstable nuclei emit particles and or energy. When we say particles, we are referring to alpha and beta. And when we say energy, we are referring to gamma radiation, and or energy to become stable. That's the definition of radioactive decay or radioactivity. And it works like this. When you write CSEC, we call that ordinary level. Ordinary level. You go through this process, which is called CAVE, and then you are now at the advanced level. So you did ordinary level physics, you learned the basic chemistry and physics, you learned the basic stuff, and then now at CAVE, you're getting into more detail, you're getting to the advanced level. In the same way, you have an unstable nucleus, and an unstable nucleus goes through the process of radioactive decay, and that's how it becomes a stable nucleus. Are we okay with this so far? Just let me get the feedback because
Okay.
sometimes, okay, Vish is okay with that. All right. Remember, you can also type in the chat to let me know, right? Because I don't want to lose you at any point, either in my explanation or because of connectivity issues. So I want to know that you're following all along. So Devin is following, Kiana is following, Shannon is following, Amy is Devishkar, Vish. Kiana, are you following?
Yes, sir.
Right. And Shannon, are you following? Oh, yeah, Shannon said that she is. All right, great. So moving on, where does radioactivity happen? So when we look at the structure of the atom, we see that there is a nucleus containing the neutron and proton, and then orbiting we have electrons. Radioactivity actually happens within the nucleus. So we're going to just take that part out of there. Here is where it happens. And coming in to the nucleus, there's actually two forces that are at play. And these two forces are called the electrostatic repulsion and the strong nuclear force. And this is the idea. We had said that the purpose of the neutron is to maintain nuclear stability. What that means is that the protons, positively charged, because they have the same charge, they will repel each other. That there is called electrostatic repulsion, right? That is the force that is attempting to push all of these positive charges away from each other. But to keep the nucleus together, we have the nuclear force, which we call the strong nuclear force, which is really what the neutrons are there for. And so there is a battle then between these two forces, the electrostatic repulsion. The protons want to repel each other, but the neutrons want to keep the nucleus stable. Now, there are some conditions. Like you correctly said, not all elements or not all atoms are radioactive. So how is it that we're able to tell which atoms are radioactive and which are not? And so that brings us to the stability conditions. And the stability conditions are as follows. First, we say that the red circle represents proton and the gray represents neutrons. The first condition is that any atom that has more than 83 protons is unstable and therefore is radioactive, right? Any proton, or sorry, any atom which has 84 or more, or in other words, greater than 83 protons, are unstable. The nuclear force is unable to keep the nucleus together. The protons repel each other to a greater extent. That is why they are unstable. Now, what if the proton number or any atom that has less than 83 or less protons? Then there are three conditions that we have to deal with. Definitely, if it is greater than 83, it is unstable. But what if it is less than 83? First condition, if it is less than 83 and the number of protons is greater than the number of neutrons, definitely the nucleus is going to be unstable. Now, that is so because protons, they will repel each other. And if you have more protons than neutrons, it means that the repulsive force is going to be greater than the nuclear force that is trying to hold these protons together. So if the repulsive force is greater than that glue, that thing that is trying to hold them together, the nucleus is going to be unstable. So in this diagram, you see that there are more red circles than there are gray ones. So there are far more protons present that causes the repulsive force to be greater than that nuclear force which is holding the atoms together. The second condition is if the number of protons is, and you notice there is this symbol here, this symbol is read as far less than, not just less than, but far less than the number of neutrons. So we have, as opposed to what's going on above, we see that there are more gray circles now than they are red circles. And for this one, it means that the nuclear force from the neutron is actually way greater than the repulsive force for the protons. And that also makes the nucleus unstable. So if you have a greater repulsive force than the nuclear force, the atom is unstable. If you have a greater nuclear force than the repulsive force, a far greater one than the repulsive force, the nucleus is unstable. And the only stable condition is when the number of protons is less than or equal to the number of neutrons. When we say less than, we don't mean that, okay, this is 8 and this is 12. That's going to be far less than. When we say less than, they differ by just 1 or 2 or so. That is what we mean by less than. So if you have 9 protons and 10 neutrons, that's okay. But if you have 9 protons and 15 neutrons, that will be counted as far less than. The 9 proton would be far less than the 15 neutrons or the 12 neutrons. But if it's just they differ by 1 or 2, or not even 2, maybe 1 or so, that's fine. But we don't want them to be very much different from each other. Is this explanation clear? Or do I need to clarify anything? Let me just have a feedback very quickly. Kiana is saying to repeat. What is it that you like me to repeat?
Sir, please repeat the last condition because
Okay, this is the one in which it is
the
stable.
last condition. I didn't
Right.
get it.
Okay, so it is stable.
Yes, sir.
The nucleus is stable if the number of protons is less than or equal to the number of neutrons. Meaning that if you have the same number of protons and same number of neutrons, right, the atom is going to be stable. If you have fewer protons and than neutrons, it's also going to be stable, provided that the number of protons and neutrons don't differ by much. They differ by 1 or so. It's still going to be stable. Do you get that?
Okay, thanks, sir.
Right. Okay. So again, do I need to repeat anything for the stability conditions or are we clear?
Clear to me, sir. Thank you.
Okay, great. So, for example, so look at the conditions very carefully, right? And let's see if we can predict some stuff. Uranium. Now, uranium, 2 isotopes of uranium that we have here are uranium-235 and 230. Uranium has 90, it is the 92nd element of the periodic table, 92 protons. And uranium-235 has 143 neutrons, uranium-238 has 146 neutrons. The question is, why is uranium unstable? Why is the nucleus of a uranium atom unstable based on the stability condition?
Because the atom has more than 83 protons, and because of this, the nuclear force loses its ability to keep the nucleus together.
That is correct, right? That is correct. So when we go back, we see that, okay, notice some persons got disconnected. Let's just give them a second or so to rejoin. Pause. So let's continue. Right. So as Vish is correctly saying, uranium is going to be unstable because it has 92 protons. And one of the conditions that we discussed that will cause an atom to be unstable is if it has a proton number greater than 83, right? That is what makes it unstable. Now look at this. We have three carbon isotopes here: carbon 12, carbon 13, and carbon 14. Carbon 12 and carbon 13 are stable, but carbon 14 is unstable. The reason that carbon 12 is stable is because the number of protons is equal to the number of neutrons. So the repulsive force balances off with the nuclear force that holds the protons together. Here we have that the number of protons is 6 and the number of neutrons is 7. Number of protons is less than the number of neutrons, but they differ by just 1. And because of that, carbon 13 is also stable, right? Once the number of neutrons is greater than the number of protons, but not by much, the isotope is stable. Notice that we can't apply the greater than 83 here because the amount of protons here for the carbon atoms is just 6. But for carbon 14, there are more neutrons than there are protons. There are 8 neutrons and 6 protons. There are actually 2 more neutrons than protons. And this is considered, in this case, to be a large difference. And so that there satisfies this condition actually, that the number of protons, 6, is far less than the number of neutrons, which is 8. And as a result, carbon 14 is going to be unstable, right? Now, like we mentioned, Rutherford figured that there are 3 types of radioactive emissions that the nucleus will attempt to give off in order to become stable. And these emissions are alpha, beta, and gamma. Now, an alpha emission is actually 2 protons and 2 neutrons. A beta radiation is an electron. And gamma radiation is energy, or in the form of, as we say, a photon or waves, right? These are the 3 types of emissions. We're going to get into a bit more detail with them in the next session. Just to now talk about this. How do we determine which type of decay occurs? Now from this graph, there is this red line here. And the red line indicates a 1-to-1 neutron to proton ratio, as we call it, the NP ratio, N divided by P ratio, 1-to-1. What that means is that along this line, if an element has, for example, at this point here, when we read, we see that this element has 60 protons, it will also have 60 neutrons. That is what a 1-to-1 neutron to proton ratio means. So any atom on this red line has the same number of protons as it does neutrons. Here, for example, this atom has 90 protons and 90 neutrons. This blue region here, right, is called the band of stability. The band of stability. And what the band of stability is that any atom within that region is stable. Hence the word band of stability. Anything within this region is stable, right? Now, we can have atoms above the band of stability, or we can have atoms below the band of stability. First of all, any nuclei which is greater than or equal to 84, greater than or equal to 84 is the same as just greater than 83, undergoes alpha emission. So the thing that we're talking about, the conditions for stability here, once the atom has a proton number greater than 83, the type of emission that it undergoes is alpha emission. So this here is alpha emission. Next, if the nuclei is above the band of stability, so this blue region again is the band of stability, any atom found above it, but less than or equal to 83 undergoes beta decay. There's a Tor type less than or equal to 83, but under the band of stability, it undergoes something which is called an electron capture or positron. But the syllabus says we don't have to deal with this, so we're not going to talk about that. The only two things that we're going to talk about, or the only three things, and I'll talk about gamma a bit later, is this here. If you are above 83 protons, you'll definitely undergo alpha emission. And if you are less than 83 protons and above the band of stability, you will undergo beta emission. A clearer form of the diagram is here. The purple region represents the band of stability. Any atom found within that region is a stable atom. Now, here we have atoms that have proton number greater than 83, right? Proton number greater than 83. And notice that it is below this purple region. It is below the band of stability. Once it is greater than 83, and 83 really is the element bismuth, bismuth, then you will undergo alpha decay. And what that really means is that you don't have enough neutrons for nuclear stability. There is not enough neutrons for nuclear stability. And let me show you this much. Look at this. Look at uranium, for example. It has 92 protons and 143 neutrons. Because the number of protons is greater than 83, it undergoes alpha decay. This 143 proton is not enough to keep these 92 protons together, because the repulsive force between two protons acts over very great distances. They can act over very great distances. This here is repulsion. Whereas the nuclear force between the neutron, so a proton is here and a neutron is between them, this can only act over short distances. So you need a lot more neutrons to maintain stability. So this 143, although it's more than that 92, it is still not enough. Still not enough. So again, we have, and this is how you tell whether it is an alpha emission or a beta emission. Once it is greater than 83, it is an alpha emission. And in that case, you don't have enough neutrons for nuclear stability. The repulsive force is greater. And beta is if you're above the band of stability and there are actually too many neutrons present. Then we undergo beta decay. In our next session, we'll talk about this in more detail, and we'll also talk about gamma emission. That is the end of today's session. Let me know if you have any final question, comment, something that you previously did not understand because I know you guys mentioned that you did all of this already up to bonding. So just some general feedback. Anything that you have to say before we